Okay, so thank you all for coming here tonight, and so thank you for being here. When I was first asked by Mark and Deja to give this talk, I had no idea what this is, and so I didn't know, should I give kind of past work, future work, what is it? And slowly, as kind of the date approach, I started to realize, oh, this is a big deal at EPFL, you know, and now Rudiger mentions that, oh, we haven't done this in a while, and then I realized that actually, I have not given a live lecture not lecture, I've given lectures, but a live talk in 3 years, actually, since COVID. So this is also my first. Okay, so I'm going to talk at a very high level about some of the projects that we do in our group on wireless kind of networking and sensing. And before I start, I'm going to acknowledge kind of my students and my group because they're the ones who do all the heavy lifting, who kind of get things done, who spend nights debugging and weekends. And most importantly, they're the ones who kind of resist the urge to kind of get a hammer and smash all this expensive hardware because it almost never works and it's very frustrating. So this is what I'm going to present is their work. Okay. So wireless connectivity kind of is everywhere these days, and kind of with IoT, the numbers are kind of exploding in terms of how many devices are connected over wireless to the internet. And this should not be very surprising, as kind of IoT has a lot of applications in agriculture, kind of industry, smart cities, telemedicine, healthcare, green energy, etc. At the same time that we're seeing this boost in IoT, we kind of are seeing kind of an emergence of high throughput, kind of very low latency applications like virtual reality, kind of self-driving cars, remote surgery, robotics, UAVs, you name it. And so if you look at this, on one hand, we want to scale our wireless networks to kind of very low power, kind of thousands, tens of thousands of devices. And on the other hand, we want them to kind of support very high throughputs, very stringent requirements. And kind of this tends to be very hard. So basically, we are actually nowhere near where we want to be. And this is because all these applications of kind of wireless networks have very conflicting requirements in terms of throughput, latency, scalability, reliability, security, power, privacy, cost, form factor, you name it. So when you're designing kind of these systems, now you have to think along like these 10 different axes, and you have to figure out, okay, what is the point where I want to operate, and there's always no kind of best point. It's always a trade-off. Like even form factor, something that we don't think of a lot, but if you're talking about wirelessly connecting medical implants, that becomes very important. Or even like in 5G, people started to build these massive antennas, and then they went to put them up on base stations, and then they started to fall because they were very heavy, so no one thought of that. And so there is kind of a lot of kind of conflicting requirements, and kind of it becomes very hard to optimize kind of these networks. And so this is exactly what kind of my group does. We decided to call ourselves the Sensing and Networking Systems group, and we try to address these challenges in wireless networks and wireless sensing. And one thing that we enjoy is that we work really, as Rudiger said, across the stack. So we work all the way from the hardware up to the signal processing and communications, up to protocols and networking, going up to the application layer. And so I'm going to give you next a brief kind of summary of a lot of stuff that we've done, but at a high level, you can divide it into 3 categories: wireless networking, sensing and imaging, and IoT. On wireless networking, we've worked on mmWave networks for 5G, 6G, and Wi-Fi. We've also worked on kind of RAN virtualization and kind of recent trends in 5G. On kind of sensing and imaging, we've worked mainly on self-driving cars and kind of mmWave imaging for self-driving cars, which I'll talk about in a bit, as well as using wireless signal to do kind of non-contact food and liquid sensing. On the IoT front, basically we've worked on acoustics, voice-enabled devices, noise-canceling headphones, hearable computing, and so forth. And on the ultra-low-power IoT, we've worked on medical implants and battery-free networks like RFIDs. And there's also one kind of theme that kind of combines actually all three of wireless networking, sensing, and IoT. I'm going to put it here under networking, which is kind of joint communication and sensing for IoT, for low-power devices. And so this is kind of most of our recent work, but kind of as Rüdiger mentioned in a past life, I've worked on algorithms and collaborated with kind of people on computer science theory to develop sparse Fourier transform algorithms to compute the Fourier transform very fast. And kind of we've looked at all sorts of applications of this work in GPS, graphics, medical imaging like MRI, biochemistry. And it has also influenced a lot of the work that basically we've done recently when it comes to kind of 5G and kind of low power IoT. Now, of course, I cannot talk about all of this stuff, but I'm going to pick a few projects and just give you a high-level overview to get a sense of what kind of my lab does. And I'm going to start with mmWave because it's been a central theme in my research. And so if you don't know what mmWave is, that these very high frequencies that kind of above 24 gigahertz. So far, all our wireless networks have been operating in this region here, below 6 gigahertz. And recently, with 5G, we've opened up a huge amount of spectrum. That's more than everything we've ever kind of known. And it enables a lot of applications from 5G and 6G to virtual reality, connected vehicles, and so on. Now, if you remember from physics, if you go very high in frequencies, the signals don't go very far, if you've taken an EM class. And so basically, these mmWave signals suffer from a lot of attenuation. And to compensate for that, rather than transmitting them in all directions, what we're going to do is we're going to use antenna arrays and focus the direction of transmission. So rather than going everywhere, it's focused on one direction. And because kind of the wavelength is so small, turns out that we can build these very large antenna arrays and compress them. So on the back of my phone, I can put like 1,000 antennas, and it kind of will still be able to operate. So you create these very narrow beams that allow you to reach much farther than what you would have been able to. Now, from a networking perspective, this is actually very interesting because so far, if you think of Wi-Fi or 4G, everything has been what we call broadcast. So you transmit, the signal goes in all directions. Doesn't matter where your laptop is, where your phone is, it will get the signal. Maybe the quality will be different, but it will get it. But if you think now with these kind of mmWave radios, now we kind of are beaming the signal in one direction. So unless you're in that direction, you're not going to get the signal. And basically, if both transmitters and receivers also have these antenna arrays, then both have to align the directions. And this is a well-known problem in mmWave known as beam alignment. So how do you maintain these beams aligned between two radios? And it becomes a problem as you move around, because then you have to realign and maintain the alignment. And basically, a lot of measurement, for example, on 5G, if you've ever kind of have the mmWave kind of logo on your 5G phone and you're walking down kind of a street, you'll see that it gets disconnected a lot. And this is why, because kind of the alignment breaks. And so actually, the first problem I looked into when I became a professor is how can we quickly find the best beam alignment as fast as possible. And at the time, there was a lot of work on this, so I wasn't the first one to work on it. But then every single kind of thing out there, when we tried it on real hardware, it just didn't work. And it didn't work because all the prior work made kind of assumptions about the hardware which ended up not being true. And I don't blame kind of everyone who's done this, because the hardware at the time, like 6 years ago, was so expensive. 1 millimeter wave radio was like $14,000. In fact, I spent all my startup package on kind of millimeter wave radios. But then when you work with the real hardware, you quickly realize that you cannot make these assumptions, and you have to update your algorithms to work kind of in more practical settings. And this is what we wanted to do. We wanted something that is fast, works with real hardware, and kind of has a solid theoretical foundations. And so what we did is we came up with an algorithm that can do this in a sublinear number of measurements. And if you don't know what that means, it just means it's fast. Okay? And so we built a system around it and kind of tested it on real hardware. And if you're not very familiar with kind of computer science systems people, we tend to name our systems. So we named this agile link, kind of adaptive link. And so I know a lot of people in other areas find this very weird, but basically when you've worked on something for so long and you spent hours debugging it, it becomes like your baby, so you give it a name. And so you're going to see in every project, like there's some weird name of the project. Okay, so this was the first thing we did, and then we started to think, well, okay, how can we extend it? And turns out there's a very nice opportunity here, because with these narrow beams, we can potentially have multiple of them transmit and receive at the same time without interfering, right? And so we could add a lot of nodes and basically have multiple links transmit. We cannot do this today in Wi-Fi. If you add more nodes operating at the same frequency, you just get interference, and everything will become much, much worse. But with millimeter wave, you have this opportunity because it's directional. And this is exactly what we did. The next system we built, we called it BounceNet. And it allows you to align many-to-many beams in a distributed fashion. Okay, and of course, there's a lot of details to get this to work. But basically, we implemented this. It worked. We could scale it up to kind of 10 nodes, but then we couldn't kind of scale it much farther. Like it wouldn't work much more than 10. And the reason is some of kind of the details that I'm not telling you about is you have to account for the fact that what I'm showing you here is just like a toy figure. Really, these beams are not like a cone. They look something more like this. So there is a beam in one direction, but there's all this kind of leakage in other directions. And so basically, when this guy is transmitting, some weak signal is interfering with this guy and this guy. And so you don't really get the scaling or the spatial reuse that you want. And so we started to look at these beam patterns. And so here's a figure of them plotted in polar and kind of Cartesian. And so what you see here is the angle versus kind of the beam, the power in dB. And so you see there's a main beam, there's a strong direction, and then there's all these what we call side lobes, and these create a lot of interference. But again, there's like a nice opportunity where if you look at this beam, you kind of see these nulls, these direction where there's no power whatsoever being radiated or received. And so the next natural thing is we said, well, okay, so what if we take these nulls and align them towards the receiver, the interferer, sorry. So whatever signal comes from the interferer gets nulled out and I don't see it, it doesn't bother me. And so this is a high-level idea. So if I have an interferer from this direction, I'm going to reshape my beam to kind of null the interferer, and then I can communicate even in the presence of interference. Again, when I started this project, I thought, oh, this is very easy. I mean, people in antenna design and who've done like phased arrays know how to do this really well. And so we thought this is like a quick project. We'll finish it in a month, be done. And then you get a huge slap in the face from the hardware that tells you that, no, okay, I'm not going to give you any control, or not any, I'm going to give you very, very limited control for you to change the beam pattern that you want. And so if you try to do this on commercial hardware or hardware that's out there, it just doesn't work. You cannot create nulls very easily. And this is kind of exactly what we tried to do, and it took much longer than we thought. But we managed to create kind of, with very limited control on these antennas, create kind of these beam patterns that create nulls and remove interference. And what we did is then we took this idea and we applied it to the previous project, and what it allowed us to do is to scale much, much further in terms of, or much better in terms of the number of nodes in the network. As I mentioned, all of this kind of we tried on real hardware in kind of real test beds. And kind of we have a lot of results. I'm not going to go over them here, but the idea is we can do the beam alignment much faster. We can have more nodes kind of transmit and receive at the same time on the same frequency without interfering, and we can null interference really well. And so if you think of what we did here, we started kind of from a single link. And kind of we said how to do the beam alignment fast. And then we went up, so this was a physical layer problem. And we went up to a higher kind of layer in the networking stack and said, well, how do I manage these different beam alignments so that I can have more nodes transmit and receive at the same time? And then we realized that the bottleneck there is kind of the hardware or the antenna, so we went back down to the kind of hardware and said, well, what algorithm would allow me to set kind of the controls of the hardware to be able to get kind of better performance? So what's next? So now we're kind of working with people who kind of do VR and AR to try to kind of adapt these techniques and others to real VR, AR headsets. And it turns out, again, it's not as easy because there's very stringent requirements there depending on whether you're doing rendering or kind of offloading to the cloud or kind of depending on what you're doing or what's your application. But this is kind of where this work is heading. All right. So this is kind of one example of kind of our work in the networking side of wireless. I'm going to talk next about an example of our work in the imaging and sensing. And specifically, I'm going to talk about autonomous driving. So there is a lot of interest on getting this to work, on getting self-driving cars to work, and kind of a lot of research and a lot of investment. But kind of the standards for driving automation says that for this to work, it has to achieve what they call level 5 autonomy, which means that it has to work in bad weather. And today, it still does not work in bad weather. So unless you're in kind of sunny California, you're not going to get this to work well. So here's an example. I'm going to give you show you an example. This is a Tesla driving in clear weather. And what you're going to see is that it can detect the cars passing by. It works really well, no problems whatsoever. And then I'm going to show you an example. There's slight fog. And in some cases, it aborts, says you take control. But even worse, in other cases, you'll see the cars passing by. It doesn't even detect them. And so you don't think I picked the one example where it didn't work. Here's another one. Still kind of the cars passing by. It's unable to detect them. And so this shouldn't be very surprising because kind of these self-driving cars mainly use LiDAR and cameras, which are optical sensors, right? And so they kind of, in bad weather conditions like fog, sandstorms, snowstorms, in low light conditions for cameras, they don't work well. Now, millimeter wave, these kind of signals that we've been talking about for networking and 5G, actually can also be used here in radar. And they don't discriminate against bad weather. They're fine with it. So they penetrate through bad weather, and they can work well there as well. And so what we thought is, OK, so why is it that we don't use that? So today, most of these cars have these millimeter wave radars, but they use them only for 1D ranging. So it will tell you how far the car in front of you is, what is speed, but almost that's it. What we wanted to do is 3D imaging, like full-fledged imaging. And when we tried to do that, we quickly realized that, one, the resolution you get is way, way, way worse than kind of LiDAR and cameras. But not only that, there are problems like specularity. The reflections of your radar don't come back to you. They go kind of somewhere else, and you can never see them. There are artifacts. And so what we did is to go with a data-driven approach to say, well, okay, what if we use neural networks? And the reason we believe this will work is basically the thing we're trying to image is not some random image. It has some structure to it, right? So when I'm driving in Lausanne, like, I'm not going to see a dolphin jump in front of me, right? So it's going to be a car, a motorbike, a bike, a pedestrian. So it has a lot of structure. And so this is exactly what we did. And so what we used is a stereo camera to get kind of ground truth depth map. And then after getting the ground truth, we would have a fog machine, because we cannot always have fog, to kind of create very dense fog. We capture the signal using kind of millimeter wave radars, and then we feed it to the neural network, and kind of it gives us back the depth map. It gives kind of much better resolution. It kind of fills in the missing parts in the image, and kind of it removes the artifacts that are caused by multipath, if you know what multipath is. I mean, of course, kind of taking something that is very well established in vision and adapting it to radar signal was not straightforward. It took a lot of iterations and a lot of customization. But kind of course, one of the biggest problems we had is data. Because as you know, neural networks can consume a lot of data, and we don't have a database of images out there. And collecting kind of these takes a really long time. So what we did is build a simulator that kind of tries to, as much as possible, model the reflection from the radar. And in fact, all these results were trained with simulated data, not with real data. But they seem to generalize well to real data, which is kind of very promising. And so we continue work on this, and we kind of extended it to kind of detection of bounding boxes. So figuring out exactly where the car is, and kind of getting this system to work in real time. So the previous one we had to take forever to collect. Now we have a radar that can collect things in real time. And so here's a demo. Now the demo is not great because the range of our radar was only 25 meters, so any car beyond 25 you will not see. And we didn't do any temporal post-processing, or kind of, we didn't use temporal information. We did it frame by frame, so you could eventually improve this or get much better results if you kind of include temporal information. Okay? Great. So we've talked about networking. We've talked about imaging. And next, I want to tell you about projects that combines kind of both, not imaging, sensing, or localization, which is joint kind of communication and sensing, and it's targeted for IoT. So as I mentioned, the number of IoT devices is exploding, and one kind of key primitive in many applications, like tracking cattle, is localization and tracking, being able to figure out exactly where the IoT device is. And so I'm going to ask a question, and the question we asked was simple. If I have an IoT node, can it localize itself? Can it know its location without GPS? It doesn't have GPS. Can it know its location just by listening to kind of ambient 5G signal? So your phone is communicating with the tower, it listens to the signals, and tries to kind of figure out its location. And I wanted to do this without any coordination with the base stations and without any modifications to the 5G standard. Because as soon as we say we want to change the standard or we're going to change the base station, I mean, good luck. You will not see this happen in 20 years. Okay? So, but if we can have our own device and say, I'm just going to listen, you don't need to change anything, we could potentially do kind of have something that works much faster. And so why 5G? Why now we can do this? Well, there are unique aspects of 5G. One, it does support IoT, but more importantly, it has small cells and picocells. So rather than having one base station cover, for example, EPFL, you will have 20 base stations spread, smaller ones spread all around. And kind of you have much larger bandwidth. So with 5G, you can have a bandwidth of 100 megahertz, even 400 megahertz. And what this gives you is very accurate time of flight information. So you know exactly when the signal is coming. If the signal is coming from different locations, you know exactly the time it arrives. Now, of course, kind of leveraging this on a low-power IoT device is not easy because most IoT devices cannot capture large bandwidth. That would consume way too much power because the analog to digital converters would require you to sample at very high rates. So most IoT devices kind of sample at much lower rate, have much, much smaller bandwidth, and this really limits your resolution and your performance. So rather than getting kind of very accurate information of the time of flight, you get kind of mixed information from all the paths, and it's very hard to localize. So how are we going to solve this? And this is probably the only technical part of the talk, and I included it because it's the only part that I think everyone has not seen. Everything else I spoke about, I talked about in past kind of in the drop talk. So how are we going to do this? So we're going to sample below Nyquist. And now if you're a signal processing person, you'll say, this person, you're crazy. Because if you don't have a sparse signal, you cannot sample it below Nyquist and still recover it. But we have a secret weapon. And this secret weapon is kind of a MEMS spike train filter. So what this allows us to do, and this is not something I build, but kind of people in the MEMS community and circuits community build, but I collaborate with them. What we're going to do is we're going to take the 5G signal, pass it through this spike-like filter, and it's going to allow us to effectively stretch our bandwidth as if we have very large bandwidth when we don't. So there's two questions to answer. What the hell is a MEMS spike train filter, and how are we going to use it? So at a high level, these are kind of MEMS acoustic resonators, and the way they work is you have a piezoelectric film, and what happens is that there are electrodes on it, and what happens when you pass the RF signal, it gets converted to acoustic signal. And this piezoelectric material starts to vibrate, and then part of the acoustic signal gets kind of reflected back in the output as RF signal again. And depending on how you build this and where you put the electrodes, how far they are from each other, the size of the piezoelectric film, you can control what are the resonant frequencies and what frequencies get passed and what frequencies get filtered out. And so we worked with kind of the circuits folks, and we built this one. It had 19 spikes. They were kind of spaced at 22 megahertz, and they spanned 418 megahertz. Okay, so now how are we going to use this? So here it is. We're going to take the 5G wideband signal, pass it through this filter. It's going to just keep parts of it and suppress most of it. And what's going to happen is it's like we took a densely occupied spectrum and we sparsified it. We made it sparse. Now that it's sparse, we're going to be able to sample it below Nyquist. When we sample it below Nyquist, it gets aliased. Then we can do different things and do sparse recovery, use sparse recovery or sparse Fourier transform kind of algorithms that I mentioned to recover back this sparse spectrum. And once we have this sparse spectrum, we can actually again use sparse recovery to recover back what we call channel impulse response, or kind of the timing of these paths. Now, if you understood what's going on here, you can be my best friend, but I have to move on because I only have 1 more minute. So we also kind of implemented this, and we built kind of the setup, tested it in kind of a large agricultural field, parking area, campus, and kind of we got very promising result. And in the last minute, I'm just going to talk about one more project I'm interested about, which is in micro and nano implants. So today, people are actually building these kind of microbrain implants. They build kind of these nano implants that can swim through your blood vessel. It is a bit freaky, but it can be very useful. These micro robots that do targeted drug delivery, contraceptive kind of implants, as well as kind of MEMS labs on chip. And so one thing I'm interested in, coming from like the networking and communications background, is how do we network and communicate with these implants? And of course, kind of the traditional way we communicate with implants is using wireless. But the problem there is the form factor is too big, wireless signals don't kind of travel inside the body, and kind of it requires high-power devices sitting outside your body. So the idea is that to communicate with such devices, you would use kind of biomolecular communication. And at a very high level, like the simplest thing you can do is, for example, if I want to transmit a 1-bit, I would release some particles. And if I want to transmit a 0-bit, I would release nothing. This is like the simplest thing you can do. Of course, there's much more complex things, but basically this field has mostly been kind of theoretical. There's not much experimental work, very kind of limited experimental work, and it's kind of the performance is not great. And kind of one of the reasons I think is because this channel, everything we've built kind of was based on RF and electromagnetics, and this kind of channel is what we call diffusion channel. So it's very different. When you release particles, they kind of diffuse, they spread around, it's kind of much harder to detect them. And this is something I'm interested in, and we're starting a collaboration with a biochemist who kind of can design these cells that, they're actual bacteria cells that you can control to release certain particles at certain times. But I wanted to mention it here because basically I'm very interested in this, and if anyone kind of is doing work on kind of this, I would be very interested in talking to you. So finally, to conclude, if you look at what happened over the past 2 decades, we started from people talking on their phones to kind of connecting people to the rest of the world. And over the last decade, we moved from connecting people to connecting things. And the vision is that we're going to move next from connecting everything to connecting and sensing everything. So there's this vision of creating a digital twin, and kind of wireless sensing and wireless connectivity is actually a central part of that. Okay? Now, of course, it brings all sorts of challenges in privacy, security, communications, you name it. There's also another interesting trend, which is new with 5G, is that finally the radio access network is being opened. So we have Open RAN and virtualization, which kind of opens the avenue for much more research, which was mainly restrictive because you had to build a circuit, and that was it. So I'm going to stop here. Thank you all for coming, and I'll take questions.